Well, how's everybody doing out there? Well, welcome to day 17 of Corona Online School. So today we're actually finishing up chapter 8. So up to this point we've done confidence intervals, estimating the population mean when the population standard deviation was known, which we found out rarely ever happens. We did confidence intervals to estimate the population mean when the standard deviation or population standard deviation was unknown, which is normally the situation that we'll be in. So now what we want to do is actually use confidence intervals to estimate the population proportion of a situation. So with a proportion, unlike a mean, like we won't have like a ton of data where we have to add everything up, find the average, find the standard deviation. It's actually a lot easier. So with a population proportion, this is going to be more almost like the binomial distribution, where it's either a yes or a no type of situation. So what you'll see is like for example in this very first category. Oh well, don't worry about that right yet. But so like if you were doing something, a political poll, for example, you may ask, are you Republican or Democrat or something like that? Or are you Democrat or not Democrat? So you want it to be an either yes or no type of situation with the probability or proportions. And so all we're going to do is when we take our samples is we would get, like a bunch of things that are in favor of what we wanted. So if we were interested in finding out if you were Democrat, then that would be like our positive thing that we were interested in. And if you were not Democrat, then that would be in kind of the opposite or the negative category or whatever it happens to be. So everything's kind of a yes no. So even though it's not called a binomial, that's really what we're working with. It's kind of a binomial type of thing that we're working on. So in this case, our point estimate, our best point estimate, is going to be what's called the sample proportion in this case, which is going to be the proportion we find from the sample. And again, what we're trying to estimate is the population proportion, which stands for P. So this little P with the triangle over it is what's called P hat. So if you're referring to it, it's going to be referred to as P hat in this case. So that's going to be our sample proportion. So really the big things that we need to know in this section, it's pretty minimal, which is kind of nice, is really how many people are, kind of voting or whatever in the same direction that we were interested in, and how many total people did we actually sample in this case. And that's it. That's going to be all we need. And from there, we can pretty much do everything else. So let's kind of dive in and look at how we construct a confidence interval by hand. So if you notice, it doesn't look that much different from the first one that we did. So the first thing we need to know is we need to find the point estimate. And so in this case, our point estimate is going to be the sample proportion, or that P hat. And so again, the way we do this is we're going to take a sample of some number of people, and they're going to respond in a certain way. So the people that respond the way that we're interested in are going to be, called X in this case. And the number of people that we surveyed altogether would be sample size N. So for example, like who knows, like maybe we're working for M&M company. We wanted to know, how many people liked brown M&Ms compared to all the other M&Ms. So in that case, our X would be, oops, wrong thing. So our X would be the number of people that their favorite M&M was brown M&Ms. And so the N would be just all people that were surveyed in this case. So P hat would be the proportion of people that brown is their favorite M&M in this case. All right. So the next thing we have to do after we've found that, or it may have been given to us, it's hard to say, so is find the standard deviation of our sampling distribution. So this one's a little ugly looking and it's a little bit different. So the first thing that we need to talk about this standard deviation is we need to find this value Q hat, which is basically all the other people. So like in this case, P hat above, I'll use that as our example. So P hat was the percentage of people who like brown M&Ms. So our Q hat is going to be the percentage of people, who don't like brown M&Ms. So it's the people that like any other color basically other than brown in this case. So that's why it's 1 minus p in this case, because remember all of our probabilities add up to 100. So if I do 1 minus p, that's going to give me the other percentage that doesn't like brown M&Ms. So to find our standard deviation, we want to multiply basically our probability of success, which is p hat, times our probability of failure, which is going to be our q hat, all divided by n, which is our sample, and then just take the square root of the whole thing. So before we only square rooted the bottom, here we want to square root everything. So everything happens inside the square root. All right, is that okay with everybody? All right, and so finally, the last thing we need is to go back to that z-value and find the z-value that corresponds to whatever confidence level we're looking for. And so again, if we're doing this by hand, this is still our z alpha over 2. So this is exactly like we did in 8.1, exactly the same stuff. And so when we look at our confidence interval, it doesn't look that much different than what we had before. The only difference was in 8.1 we had the sample mean, so x with the line over it instead of p hat. And our standard deviation looked a little bit different. But otherwise, it's exactly the same formula, so nothing new. The inequality notation, again, kind of messy looking. But all I did is just kind of expand that plus minus out. And instead of having the mu in the middle, I've got the p in the middle for my population proportion. And then just like in 8.1, we had our margin of error. So again, our margin of error is still exactly the same. It just looks a little bit different because the standard deviation part's a little bit different. But otherwise, it's the same. And so if we write this out, our margin of error still looks much cleaner than the one above. But again, so if we can do 8.1, there's really not that much difference to doing 8.3. So, all right, we ready to try one and see how we do? All right, perfect. Let's dive in and check it out here. So let's look at example 1 here. So we're looking for Android loyalty. So the Nielsen company surveyed 225 owners of Android phones and found that 160 of them plan to get another Android phone as their next phone. Construct a 95% confidence interval for the proportion of Android users who plan to get another Android. So in this case, you remember the big things we need to know. We need to know X. We need to know N. Eventually we need to know p hat, but we have to know x and n first. We need to know q hat, which again we can't find until we know p hat. And then we need to know our confidence interval, which in this case is 95, which is going to help us find our z alpha over 2 in this case. All right, so our x is the 160 people that planned on getting an Android. The total number of people surveyed were 225. So in this case, our p hat is just going to be 160 over 225, which if I throw that in the calculator gives me 0.711. So in this case, so I'm just going to leave it at 0.71 at the moment just to make it a little bit easier. And so now I need to figure out my q hat, which is just going to be 1 minus 0.71, which is going to be 0.29 in this case. And so now I need to find my z alpha. So remember, our z alpha is going to be, if you're doing it by hand, that's where you have to do that weird tricky part where you're not actually plugging 95 in, because 95 is only the middle part. We have to account for the part on the end. So if you remember, in this case, 100 minus 95 gave us 5%. If I divide that by 2, then that means that there's 2.5% below the 95. There's 2.5% above the 95. So when I want to use the inverse norm, I need to add 95 to that 2.5 to figure out my percentage. So in this case, 0.975, and then 0, 1 to get my z-score that I'm looking for. So let me jump back to the calculator here real quick. So second vars, inverse norm, 0.975, 0, 1. equals, so 1.96, which we probably wrote down anyway, but just to show you again in case you forgot. So in this case, my z alpha over 2 is going to be 1.96. So now I've got all the information I need to come up with my confidence interval in this case. So just to kind of jot it down, so I'm going to look for p hat plus z alpha over 2 times the square root of p hat. Oh, goodness, that's terrible. It's kind of ugly looking. So p hat times q hat, all divided by n in this case. And then at the same time, I'm going to do the minus of these guys. So I'll do the minus underneath. So let me fill out what I've got here. So I've got 0.71 for my p hat plus 1.96 for my z-score. And then square root of 0.71 times 0.29, all divided by the square root of 225 in this case. So this is going to be my upper limit for my confidence interval. So this is going to be my upper because it's the plus. So let's plug all this into the calculator. So I'll show you how to type this in so that way we hopefully get it right every single time. So in this case, what we want to do is we start with our 0.71 plus our 1.96 times, and then square root, so second x squared. So in this case, what we're going to want to do is put parentheses around the top. So it's possible yours will work without it, but just to be safe, you're better off putting the parentheses around the top just to make sure the order of operations work out right. So 0.71 times 0.29. So there's my p hat times my q hat. Then in parentheses divided by my 225. And then just hit enter. So it looks like 0.76 or 77 would be my upper interval in this case. So 0.77. So my upper is going to be 0.77, or about a 77% chance of the upper. So now let's do our lower. And so our lower is just the same thing, but just the minus. So I'm going to get 0.71 minus 1.96, and 0.71 times 0.29 all over 225. So again, throwing this into the calculator. And so I'm going to cheat again, so I'm just going to hit second enter. So all I have to do is just go back and change that plus to a minus because I'm lazy, and if the command's there, why not use it? So hit enter. So it looks like 0.65 is going to be our lower percentage. So our lower estimate is going to be 0.65. So now writing this in interval notation, or in inequality notation, I've got 0.65 is going to be less than p, because remember we're trying to estimate the population proportion, so I don't want to use p hat here, I want to use regular p, less than 0.77 in this case. So what it's saying is that the majority of the people are going to be, so the population proportion is really going to be somewhere between 65% and 77%, with 95% confidence are going to get another Android phone in this case. And so in this case, if we look at part B, it says assume that an advertisement claimed that 70% of Android users plan to get another Android. Does the confidence interval contradict this claim? And so the good thing is it looks like no, because 70% clearly lives in between 0.65 and 0.77. So that seems like a good it seems like a good claim to me. So in this case, no, it doesn't contradict the claim. All right, perfect. So take the next couple there. You guys practice those on your own a little bit. So again, if you get stuck on them or anything like that, let me know. So take a break, pause it real quick, work on these guys. And then when you come back, I'm going to show you how you can use the calculator as a way to do these. And not just finding the z-score, but finding the whole thing. And so, because there's a nice command that actually does all this for us in this case. So when you're done, come on back and we'll work on the next example. All right, hopefully everybody's doing a good job out there. So now let's figure out how we can do this using the calculator. So I've already kind of given you a hint that the command we want to use is what's called one prop z int. So in this case, it's one probability or one proportion z interval is what it stands for. And it's in the same place that z interval and t interval were, so we know exactly where to find it. And the cool thing is there's really not too much stuff you have to type in to actually make this work, which is really kind of nice. So really just looking at the x, the n, and the confidence interval. Once we know those, we're ready to go. So let's take a look at example 2, and then we'll plug it into the calculator just to see what we get. So according to the U.S. Census Bureau, 43% of men who worked at home were college whoops, I meant to highlight that. 43% of men who worked at home were college graduates, and a sample of 500 women who worked at home, 162 were college graduates. Construct a 98% confidence interval for the proportion of women who work at home who are college graduates. And then the second part is related to the 43% of men in this case. So don't worry about the 43% of men yet. We'll answer that when we get to, is it reasonable to believe? That part's really good. It's kind of comparing the proportion of women that work at home to the proportion of men and seeing if it seems reasonable. All right. So again, let's write down what we know. So in this case, our x is the number of women who worked at home that were college graduates. So that's going to be 162. Our sample was n, which is 500 women who actually worked at home. And our confidence interval that we're interested in is 98%. All right, so let's remember those numbers. So now what we want to do is go to our calculator. Let me clear that real quick. So go to Stats, go to Test, and then if you look, letter A is our one prop z int. So if we click on that, so again, if we notice over on the left-hand side, all it's asking for is 3 things: what x is, what n is, and what the confidence level is. And so, what was it, 162? I think I forgot. There we go, 162. 500 for our n, and we wanted a 98% confidence level. And so the cool thing is, not only does it actually calculate what the lower and upper is, it also tells us what the p hat is for the sample. So it also gives us the sample proportion without us having to find it on our own, which is kind of cool. So in this case, our lower looks like 0.28, and our upper looks like 0.37. Let's write that down real quick. So 0.28 less than p less than 0.37. Or again, if you like writing these as percentages, you could write them as 28% is less than p is less than 37% in this case. So that's the probability that a woman is going to work from home and have been a college graduate. Somewhere between 28% and 37% of women would fall into that category. So the question is it reasonable to believe that this is the same as the proportion for men? So in this case, is it possible that really 43% of women work from home, have college graduates? So it seems pretty unlikely. I mean, based on this sample that we did. So, I mean, it's possible that we got a bad sample. You know, that always is a possibility. So we can't conclude 100%, but this looks to be that 43% is definitely going to fall outside of that 98% confidence interval. So we're 98% confident that, you know, a woman that's a college graduate and working from home is going to be between 28 and 37%. So it seems pretty unlikely that there would be a 43%, I mean, based on our sample in this case. So this seems unlikely. That the percent could be 43%. So, all right. So with that in mind, the rest are just a bunch of practice problems for you guys. Oh, there is one more. Sorry. So practice 3 and 4 here real quick. So again, use the calculator just so you can practice both, and then I'll have some extra practice at the end that you can do either way you want. So if you like doing it by hand, do it by hand, and if you want to use the calculator to check yourself, that's a totally great way to do it. If you just want to do the calculator all the time, that's fine too. I'm not going to tell you one way or the other how to do it and stuff like that. So let me do the last example here. I almost forgot about this. So the last example, and we did one like this in 8.1 also, was trying to work backwards and trying to figure out, if I want a certain margin of error, what, how big should my sample be in order to kind of guarantee I get the margin of error that I'm actually looking for. So now in this case, I actually solved the margin of error equation for you. So you wouldn't have to do this, like if you don't want to memorize another formula or anything like that. If you just remember, the margin of error formula just looks like you could just plug in everything you know and solve for n, or you could do it ahead of time first. So it's up to you, like however you want to do it. I mean, the formulas are here if you want to use them. If you don't want to memorize another formula, you can get the same answer just from here by plugging in everything that you know and kind of working backwards to solve for n. So since the formulas are there, I'm just going to use them in this case. But again, it's up to you. You can do these however you want. So, and if somebody wants to see me solve it this way, just let me know and I can do it that way. So just tell me and I can make a video showing you that also. All right. Now we do have to be careful in this case because notice there are two different formulas going on because sometimes we won't necessarily know what p hat is. So the first example is if we know p hat is given, and because if we know p hat, then we know q hat. So the second example, what they're doing is if we don't know what p hat is, then what we're really doing is just kind of estimating and saying, well, let's assume p hat is 50% and q hat is also 50%. And so if I multiply those guys together, that gives me 0.25. So that's where that 0.25 is coming at in the formula. So if we know what p hat is, everything's great. We just use p hat and use that formula. If we don't know what p hat is, then we're basically just assuming that there's a 50-50 chance that you like it or don't like it. So again, it may not be exactly correct, but it's going to be close because again, if we don't know what the p hat is, this is the best that we can do. We can just kind of assume that people are 50-50 about whatever it is that you're studying in this case. So again, that's where the 0.25 comes from in this example. All right. So in this case, suppose a polling company wants to ensure that their next political poll has a margin of error of 3 percentage points. Let me highlight that. Or less. So using a 95% confidence level, how many voters should the company poll to make this happen? And so in this case, let's write down what we know. So we know we want our margin of error to be 3% or 0.03. We know our confidence interval, we want to be 95%, and we just saw that that means our z alpha over 2 is 1.96. But unfortunately, if we notice, p hat and q hat are sadly lacking from our example in this case. So since that's the case, since we don't know p hat and q hat, then that means we want to use the second formula to calculate our sample size in this case. So we want to use the n equals z alpha over 2 squared times 0.25 all over our margin of error squared. So now it's just a matter of plugging everything in and then using our calculator. So our z alpha over 2 was 1.96 squared times 0.25. And then all divided by our e squared, so 0.3 squared. All right, so let's plug this into the calculator, see what we get. Oops, hold on, I wrote that down wrong. That would have been bad. I know one of you guys would have caught that. There we go. That would have made for a totally different answer. All right, so let's plug this in, see what we get. So let's include out of here. So 1.96 squared times 0.25, and then divided by, so parentheses 0.03 in parentheses squared. So in this case, it looks like we'd have to sample 1,024 people in order to get the margin of error that we were interested in. So in this case, I got lucky. Mine turned out to be a whole number. If it's not a whole number, you should always round up for certain. So even if it's like, if this would have been 1024.00000003 something, I still would have rounded it up to 1025. So the goal is you should always round these answers up just to make sure, because you can always sample more people. I mean, it just make your margin of error even a little bit smaller, but you definitely don't want to round down for any of these margin of errors when you're doing these guys. So always round up. So kind of keep that in mind. So I got lucky, and mine was a whole number, but let me write it down here just to really emphasize it. So always round up. So regular rounding rules do not apply when it comes to finding sample size. Always round up. And that doesn't look like round at all. So let's see. I'm so excited about rounding up here. I can't even spell. So it still doesn't look like it. But anyway, round up. All right. So this time I did give you one to practice. So this way you can actually practice the sample size, since I didn't provide you one in the 8.1 section, so you can play around with. So otherwise, and there's some more practice problems at the end that allows you to practice, either doing it by hand, using the calculator, and then making some assumptions based on those confidence intervals that you found. So if you have any questions or anything like that, or if you're struggling with this, definitely reach out to me. Let me know. I'll be around the computer all day tomorrow just waiting for questions. So good luck and have fun.